So the goal of our lesson today is to take the idea that we saw in the last lesson about general end behavior and expand it to an idea of, instead of having to see the picture or the numbers plugged in, could I know the end behavior of a graph by looking at its equation? So the overall idea of this unit is that we're going to be graphing some pretty complicated rational functions. So when you look at these three equations here, these are examples of rational functions. So the definition is that it's one polynomial function over another polynomial function. When you look at these three examples, some might look familiar, some might look really odd. So you'll notice this first one, its end behavior on both ends seems to kind of average out at this horizontal line around 1, where this second one, which basically looks like a line with a hole in the middle of it, has a right end that heads up towards infinity and a left end that goes down towards negative infinity. And in this third example, again, the ends tended to settle out looking horizontal right around 1. So my goal is, if I'm supposed to build this picture, can I look at this equation and know ahead of time that I expect it to average out about around 1 so that I know this to help me build the graph? So we're going to look at different styles of equations. So I've taken 12 equations and I've put them into 3 groups. This is your first group of equations. And we're going to look through and we're going to look at the end behaviors. And then we're going to see if we can look at the equation type and the end behaviors to kind of have a hypothesis about how these behave. So the first question asks, in the first 4 equations, what's a true statement you can make about the degree of the numerator compared to the degree of the denominator? So if you remember degree of polynomial, in this first function, the degree of the numerator is 2, where the degree of the denominator is 1. In the second function, the degree of the numerator is 4, where the degree of the denominator is 2. In the third function, the degree of the numerator is 2, where the degree of the denominator is 1. And in the last one, the degree of the numerator is 4, where the degree of the denominator is 3. So when we look at these and we compare them, what we see here is that in all of these functions, they're written where the numerator has a higher degree than the denominator. So the numerator degree is more than the denominator degree in all of these questions or equations. So next we want to know is like, okay, so they all have the same type. They all have a higher degree in the numerator than in the denominator. So let's look and see if that tells us anything. These kinds of functions have a certain kind of end behavior. So if you remember from end behavior, this is a chart of numbers. You're kind of looking from the center and you're looking as you go towards the right, which this would be going towards the right according to the x values, and going towards the left. You're looking at what's happening with the y values. And here we're seeing from 5 to 50, 500 to 5,000. So what I'm seeing here is I'm seeing large jumps in the y value, and they just keep getting drastically larger. Later I'd expect to see 50,000 and 5 million. So I basically see that the number is headed towards infinity. When I look the opposite direction here, I see the numbers headed towards negative infinity. So I want you guys to pause the video for a minute, and I want you to see if you can fill in all of the different end behavior values here, and then I'll have the answers in, and then you guys can see what the answers are. So here are the answers that you should have gotten as you looked at the different end behaviors. And so what we're seeing here is I don't really know when the infinity should be negative or positive, but you're seeing that on the right end and at the left end, all the ends are going towards negative infinity or infinity. So the end behavior goes to infinity or negative infinity in all of these cases. So would you expect these types of functions to have a horizontal asymptote when they're graphed? So I'm going to take you back to the pictures we looked up at the top. Notice that in the first picture, I said it kind of settled at 1, and I would expect there to be a horizontal asymptote at 1, and same with the third picture. The one picture here that had end behaviors going towards infinity and negative infinity, I wouldn't expect there to be any horizontal asymptote there because the ends are not ending like a horizontal line to follow, so I don't need a horizontal line to follow. So because the end behaviors of this function are going towards infinity and negative infinity, when it asks me if I would expect them to have horizontal asymptotes when graphed, I would say no. And again, the reason is they don't follow a horizontal line at the ends. Okay, so we're going to look at two other types of groups of equations and do the same thing. So here's our next group of 4 equations, and we're going to ask the same exact question. So the first question is going to compare the numerator degree to the denominator degree. So we're going to go back through each of the functions and look at the degree of the numerator compared to the degree of the denominator. In the first function, they both have a degree of 1. In the second function, they both have a degree of 2. In the third function, they both have a degree of 2. And in the fourth function, they both have a degree of 3. So the equations that we're looking at here have equal values in the degree of the numerator and the degree of the denominator. Now we're going to go and we're going to look at the end behaviors in the chart. So I'm going to do one, and I'm again going to have you guys pause and think. So again, kind of looking at the middle as we go up, what's happening. So notice these values start staying really close together. They're slightly different, so like from about a 2.5 to a 2.05 to a 2.005. So eventually, if that pattern continued, I'd expect to see something like a 2.000005, which is basically like having the number 2. When I look at it from the other side, I see that at first it changes a bit, but then these numbers look really similar, especially these last two. And it goes from a 1.4 to a 1.9 to a 1.99. So I would expect later for it to be something like 1.9999999, which would be, again, like having 2. So again, go ahead and pause the video here, and then you'll be able to come back and compare if you have the rest of the end behaviors correct. So now we're going to look and see if you got these right. As I look at these, this one seemed to level out at 0.2. This one seemed to kind of stay at negative 0.3, but the 3 looks like it's going to start repeating forever on both ends. And this one at 4. So we're going to go ahead and we are going to make a conjecture about the end behavior. So notice here the end behaviors don't go towards negative infinity or infinity, but both ends do seem to stay at the same value. So the end behavior tends to kind of end at a specific number. So both ends go toward some number value. That's kind of as good as we have right now. So would you expect these to have a horizontal asymptote when graphed? My answer would be yes. And I'm going to take you back up here to the pictures that we looked at. And I actually think both of these equations, the first one and the third one, should fall into the category we just talked about. I can see that their degrees are the same. And I can see that their end behaviors ended at the same number on both sides. And in both of these, it happened to be at 1. So they'd be part of this category here. Lastly, we're going to look at a final group of equations. So the only way we haven't compared the degree of the numerator and the degree of the denominator is when it's bigger in the denominator. So here you can see a degree of 0 in the numerator, but 1 in the denominator. Here 1 in the numerator, but 2 in the denominator. Here 2 in the numerator, but 3 in the denominator. And here 2 in the numerator, but 3 in the denominator. So in all of these equations, the numerator degree is less than the denominator degree. And now, again, we're going to look at the end behaviors. So these get a little tricky, but see how you see big changes, and then these ones seem to be staying closer. So look at what it changes to, something like 0.4, then like 0.04. If you picture this continuing to keep pushing that 4 back, you're picturing numbers like this. Those numbers would basically be rounded to 0. And then I see the same thing on the other side. I see it go kind of some random numbers, and then I see a negative 0.3, negative 0.03. So if I picture that pattern continuing and seeing more zeros after that decimal and looking at something like this, even though it's negative, such a small negative number, it would basically be rounded to 0 as well. So take a moment to pause the video and fill in the other end behaviors, and then come back and check and see if you get the same. All right, so when you guys look at this, you should see that same pattern of more zeros behind the decimal in each of these, which is telling us those are going towards 0. And you see the same thing happening on this side here. So here, not only did the ends go towards a number, they just all went towards 0. So when I make a conjecture about the end behavior here, I would say the end behavior goes to 0. Whereas the last category I said a number, this one is specifically 0. So would I expect them to have horizontal asymptote? Yes. And what I would expect is that it wouldn't just be horizontal anywhere. It would specifically come down and be almost hitting the x-axis because it's trying to even out right there at 0. All right, so we're going to write these as our conclusions. So our 3 categories. So that investigation hopefully helped you understand. And the idea is every rational function that we look at is going to fall into one of these 3 categories, where the degree of the numerator was greater than the degree of the denominator, it was equal to the degree of the denominator, or it was less than. So examples here, you're thinking about a function that's fractional, and in this case you would want a higher degree in the numerator. And we said there was no horizontal asymptotes here. So how would you find one? You don't. So you guys are going to find another asymptote in this situation, which we'll talk about in the next lesson, which is called an oblique asymptote. So if it doesn't go in a straight line, it goes slanted, and we'll talk about how to find that. If they're equal to each other, that means that we're looking at something like this. Okay. Is there a horizontal asymptote? We said yes. So how do you find it? So this one was a little tricky. Let's go back and look at the numbers. They were different numbers here. This one would have a horizontal asymptote at 2, this one at 0.2, this one at negative 0.3 repeating, and this last one at 4. So remember, I don't want to have to do all these numbers every time. I want a rule that kind of helps me, by the look of the equation, know what's happening. So there is actually a really remarkable relationship here. Notice the coefficients of the highest degree terms. So in this first function, it would be 12 and 6. In the second one, it would be like a 1 and a 5. In the third one, it would be negative 3 and 9. And in the fourth one, it would be 8 and 2. These are the coefficients of that highest value that was determining that degree of the function. Now look if I just take out those numbers. Here it would be 12 over 6. Here it would be 1 over 5. Here it would be negative 3 over 9. And here it would be 8 over 4. If you actually do the arithmetic with each of those numbers, you'll notice that 12 over 6 becomes 2. 1/5 is the same as 0.2. Negative 3/9 is the same as negative 1/3, which is negative 0.3 repeating. And I'm sorry, I wrote this last one incorrectly. I thought my pattern went wrong. This should actually be 8 over 2. See, there was a 2 here. I just wrote it wrong. I got a little ahead of myself. And now 8 over 2 would give us 4. So when we're looking here about how we would find the horizontal asymptotes, we want to use the lead coefficients of the polynomial in the numerator and denominator. And what I mean by that here is like this. The one in front of x cubed for each of these. So in this example, my horizontal asymptote would be 1/5. The last category was when the numerator had a degree that was less than the denominator. So something like this. And we said, yes, there was a horizontal asymptote, and that was kind of the nicest situation because it just automatically ended up at 0. So again, your goal here, it helped us kind of review the patterns we saw before, but really we want you guys to know these conclusions right here. When we give you an equation, like one of these here, we want you to be able to analyze the degrees, know which one of these categories it falls into so that you can quickly find what the horizontal asymptote is. That's what our goal is going to be. So on the homework assignment you're going to be doing for this, you're going to be identifying if things have a horizontal asymptote and if they do, what it is, because you're going to be trying to practice these different categories.